Thank you everyone for coming. Today we have Andreas Fell from ANU. Andreas did his PhD in Hanover. He's developed a laser doping simulation tool that I used in my PhD. So Andreas was very kind while he writing his thesis, have a baby, also to simulate stuff for me. So thank you for that. We moved 3 years ago to ANU and continued to work on laser doping more on the practical processing part this time, and also developed the quad cup that everyone knows from PD Lighthouse. So I hope that everyone knows this great tool. So please welcome Andreas.
Well, thanks very much, Tiff, for the introduction. And also thanks very much for the good selection of Tim Tams you sent me after I did those laser doping simulations. So I ate them all before I finished my PhD, so that's all right. So I want to talk to you today about it's actually my fellowship I got from ASI, which I'm working on, which has a topic to develop some laser-doped emitters, or in a more general term, laser-doped contacts for silicon solar cells. And it's kind of fundamental research and proof of concept stage. So what I'm focusing on within the whole group, of course, and we'll also try to show in this talk is how we can characterize those kind of laser-doped contacts, and also what kind of efficiency we can expect if they're integrated into a sensible concept. So I want to acknowledge some co-workers. So this is Evan Franklin, who is kind of leading the laser group at ANU, and Daniel Walter, who just finished his PhD students. He done a lot on the PL characterization side. And Klaus Weber is a former supervisor and also very involved in scientific discussions. There are other PhD students not mentioned here who have some influence, but they will hopefully be referenced or acknowledged throughout the presentation. So here's how I want to structure the talk. So first, I want to explain you what, in this context, I mean with localized contacts, which might be quite different to what other image or picture when they're talking about localized contacts. And then I want to show you some simulations, a whole bunch of simulations where this new Quokka tool I developed comes very much into play, to see whether there is some good potential for those kind of cells where we involve those laser localized contacts. And after that, when we hopefully decided it's worth to go into research for that kind of thing because efficiency potential is there, the task becomes to characterize those features for efficient development. So we'll show you some characterization methods which are not quite straightforward and which we developed during the fellowship. And then at the end, I show you some cell results. So we also already did the first batch of solar cells with featuring those only laser localized contacts. So the idea is based, I will show you later on a bit why, but the idea is based to do a IBC solar cell, so an interdigitated back contact solar cell, with a localized diffusions and contacts only, where the diffusion is basically restricted to the contact opening as well. So this idea is not pretty new, so you can't blame me for that being a bad idea. That was already proposed by Swanson in the 1980s. They used it for highly concentrating solar cells, but later on, as you all know, that converged into the sun power technology. They don't use localized diffusions anymore, obviously, but still. So the idea is, or what I want to make clear in this concept, is firstly, you should know that whenever I talk about the localized contacts, I actually mean the entity of both the highly doped region underneath the contact opening and the contact opening. So it means the interface between the silicon, highly doped silicon region and the metal. So, and there's some other things we need to consider, or which makes our life a bit easier actually in characterizing and describing those features, which is because they're relatively small. So typically we're looking at laser features, so they can be as small as a couple of micron, but they are probably definitely well below like 100 micron or so. And because of that small size, what you can do, you can very well describe it by an integral property. And the decisive properties of those contacts are the recombination, which can be expressed by a dark saturation current, and the contact resistance. So the thing is that even within the contact, sorry, that was the wrong mouse. So within that contact, your recombination property might change a lot For example, here at the edge, that is still a bit passivated, and in the inner, at the actual contact opening, it's not passivated. So you might have actually very largely different recombination properties within that small contact. But actually, it turns out it doesn't really matter. So in whichever way you kind of distribute your total recombination within that contact, the only decisive thing for the cell performance is the total recombination current. And this is true because it's small, so any kind of lateral variation will effectively smear out with the impact on the device. So we've proven that by simulations, but you can also do some estimations, some analytical estimations, and see that it's valid. But because this is untypical to describe things in solar cell terms, unless you're going for a full cell, but it's not meant to be a dark saturation of a full cell, but really specific to the contact. And because also for simulation will be used a lot in that work, this is not a handy input. We actually assume, and throughout the work, we always present those properties as area average properties, so like the dark saturation current density and the contact resistivity. And this is valid for simulations. So whatever that total saturation current might be, you can always, for the simulation, you can always assume that it's evenly distributed throughout the size of the contact and assume an area average constant dark saturation current density. And that will have the same impact on the device as I just told you. But in reality, that doesn't mean that it has to be the case like that. Anyway, and yes, so the really decisive properties of the contacts, that's what I want to take you away from that slide, is the recombination property, the contact resistivity or contact resistance, and the size of the contact is also important. And for the size, because it influences like crowding effects, carrier crowding inside the device. So the important size is not so much the contact opening, but it's really the size of the doping underneath. So that defines your collection of carriers, and that defines how the current crowding happens here. So if you have the three things actually, the recombination, the contact resistivity, and the size, you have fully described, or well enough described your contact to judge the impact on the device. And you can then run simulation and see what kind of efficiency you might get with that and that cell concept. All right, now we want to do those localized contacts by laser, as I just said. So there are a few considerations we can make. So first, what kind of cell can we make with laser localized contacts only? So the first thing, or maybe the first thing you might think of, well, to get a good collection, if you only have localized contacts, you can't put them far away because then your collection breaks down because you will have bulk recombination, surface recombination. So you need to have a reasonable small pitch between the contacts to collect most of your generated carriers. But that also means because of the small pitch, so that's typically must be much smaller than the diffusion length, and the typical diffusion length in a state-of-the-art cell is much less than a millimeter or so. So you can't have that on the front side, because if you would have it on the front side and say 100 micron pitch, you would lose everything by shading of the required metal contacts. So really the only option is to put that on the rear, where you can allow a small pitch. But having it on the rear means you have a rear junction cell concept. And for a rear junction cell concept, it means you have to have a high bulk lifetime and also a very good surface passivation, particularly at the front, to not lose short circuit current and voltage, of course. So rear junction cell is more sensitive to recombination properties. So what you end up, basically, you have no choice than to go for a high efficiency device. So there's no point in taking a very costly 5 millisecond N-type wafer and then throwing some crappy laser doping process in it and come up with an 80% solar cell. So nobody would be interested in that, I think. So what we're interested in is really some high efficiency cell device, and with high efficiency I mean maybe 23, 24% with a rear junction solar cell concept. And rear junction most likely means IBC concept. It could still have front contacts, but they might prove to be difficult as well. So what's the advantage of doing that with a laser? So a laser is localized in nature, so it's actually more difficult to do large area with a laser. And particularly if you go for localized laser processing only, that is at least potentially very low cost because the laser processing tools have a high throughput. And it's also very simple. So ideally you could create the doping and the contact opening at the same time. So that would be a very easy process, and therefore would also mean it's a low cost process. And also, which I shall stress later on a bit more, you have because you have only a low area fraction of those laser doped regions, it actually allows for a relatively high recombination of that region. And that means that laser is actually of interest because unfortunately it is true that it's difficult with a laser to reach recombination properties comparable to diffusions. So this is an important point that you can accept actually quite some recombination. So of course there are challenges to this kind of idea. Firstly, one thing which goes for any IBC cell concepts, which will not be addressed, or at least not in the talk, is the metallization thing. Of course, you have to ask, of course, sun power, so it can be done in industry, but is that really a low-cost thing, an IBC cell in itself? So we'd hope that other groups maybe come up with good ideas to make that cheap. But then the other more physically fundamental problems is, as I said, because it's a rear junction concept, and recombination also suffers the JLC and also the fill factor, the collection efficiency. So the meaning is for things, for typical laser process features, so with the performance you can get from them, is there any sweet spot at all going for localized emitters only? So can you get high efficiencies? So we'll address that in the simulations. And then the real challenge, of course, becomes to develop those kind of laser processes which reach the desired properties. So now you have essentially two options to do your laser localized contact. So either the very easiest ones I just mentioned would be to go for a single pulse. So you somehow deposit a dopant source on top of your dielectric layer, and you fire a laser pulse, and the dopant gets incorporated into the silicon and opens up the dielectric film at the same time, and you're finished. Well, that sounds easy, but particularly different to like typical laser doping applications, for example, like selective emitters. In this concept, there's no existing diffusion in the first place. So what you end up is very likely at the edges, you will destroy or depassivate your surface, or destroy the surface passivation, but not have any doping underneath, which necessarily ends up to high recombination. There are some initial results that it's actually not necessary. So there might be actually a scope for doing those kind of single step processes. In particular, interesting is if you have a dielectric film which has the dopant already in it, so then it's in direct contact. So like Fraunhofer-Ise published those pass-dop things. Although if you look in detail, they never have really awesome recombination properties. So this is a big field of fundamental research, I think, to develop those kind of laser processes with very good recombination properties. But then the more conservative approach would be simply go for what we call a two-step process. So you do your laser doping kind of as a first step, then you remove the doping source whatsoever, then you deposit your dielectric film, and then you do a second laser opening step where you just remove the dielectric within a restricted area on top of the doping. So that's quite possible. Of course, that's much more complicated, and the industrial aspect of it, that it's much less feasible. There are alignment issues, and of course you have the two process steps. But from a lab-based point of view, that's the thing you want to start with because it's more conservative and likely to be successful. So that's the first thing we focus on, and also I will present cell results with this kind of process. All right, but here also it's important, that's why I stressed before that the recombination properties are not so important where the recombination actually occurs. So even here, if all recombination only occurs at the edges of those regions, we can still describe it by a total current, saturation current density for the sake of the simulation. Now, so ANU is not the first one to think of such cells. I guess anyone who worked in laser doping had the dream of doing an all laser doped, all low temperature processed solar cell with both polarity dopings and make a high efficiency cell out of it. And a group which come particularly close is UNSW maybe also, is the University of Stuttgart. They just recently published a 22% solar cell, which, well, where all the decisive diffusions or surface dopings, I have to say, were done by laser doping. So they made large area phosphorus doping and large area boron doping, then passivated the whole rear surface, and then opened up with a second laser step, metallized it and could reach 22%, which is quite impressive. So that's kind of a good motivation also for us that it's not a complete silly idea to do something like that with laser doping. A question in this cell concept is the laser doping throughput, because you have to have a really large area. I think that might be quite possible, but at least so far you can't buy a tool, I think, that will do that kind of stuff. And also if you go for very high throughput, large area laser doping, that's quite a bit of thermal power you put on the wafer, so it might bend or whatever. So there are some issues with it. And also the challenge is that the laser doped area itself, well, both laser doped areas, the boron and the phosphorus, are passivated by the same passivation, obviously. And both need to show very good chain odds because, yeah, they cover the whole surface. Which can be done, obviously, up to 22%, so it's not impossible. So here's the thing we want to pursue further. It's just going localized with all the diffusions, both the N and the P diffusions. So the advantages would be that in terms of recombination, so most of the surface area would be just undiffused, which is quite easy to passivate with a couple of passivation options. So it's relatively easy to get low surface recombination besides at the localized laser doped features. But of course, then the real challenge is again the edge regions, particularly of the laser doped regions. And in the end, that should have much higher throughput potential. So if you find a suitable process with single laser pulses or something, then laser throughput should not be an issue anymore. And I believe that the final efficiency of such a concept should also be higher when you involve laser doping, because it's just too challenging to create excellent doped regions with the laser. I have also say that on the left-hand side they use thermal oxidation for passivation, which has quite an annealing effect, and might be also questionable whether industry wants to do that. All right, now let's see. So is there scope for such a concept where all the dopings are localized? I said the challenge is to get the collection good and also the resistance losses, because all the carriers have to crowd to the small contacts. So is there any reasonable sweet spot to get a good efficiency? And for that I will present a first very optimistic, or like an upper limit simulation, which is done with Quokka. So Quokka, for people who might not have heard it, it's a 3D device simulation program which are written in MATLAB and which you can download on PV Lighthouse. It's updated regularly, I hope. So, and you can, it's exactly suited for that sort of stuff. So what we assume here for this set of simulations, we assume an intrinsic 1.5 ohm centimeter N-type wafer. So at least the 1.5 ohm centimeter N-type is something which is industrially feasible. You probably don't get an intrinsic one, but it turns out you get quite some good material, actually even industrial. In industry, could be a couple of milliseconds. So the second harsh assumption is that we assume no surface recombination besides the laser localized feature. And then also another harsh assumption is that at the front side, it's actually at the picture is at the rear side. That is because Quokka always has the junction or the emitter at the front. So to simulate a rear cell concept, a rear junction cell concept, we have to split the illumination to the rear. So actually the rear side is illuminated. So I would call it the front side. So the front side here has no shading, but is still at the same time fully contacted and has no recombination. So that's quite unphysical, but that's all right for a first kind of upper limit. That's actually the only assumption you can do for a real upper limit simulation. So and the only thing which influences or which limits the device performance is really this local feature here, which forms the emitter. So this is a P-type region, which is contacted, and we vary the chain out of this region and the contact resistivity and see what efficiency we can get. Now for a fair comparison, for each pair of chain out and air cont, you have to find the optimum efficiency. And that means the optimum efficiency in terms of the pitch of the contacts. So for each value pair, actually the pitch has been optimized in the following plot. So what you get, simulated that for two different cases, one for smallish contacts, 30 by 30 micrometer, and another one for a bit larger contact, 75 by 75 micrometer squared. And you see a surface plot of efficiency. And yeah, what I want to point out here, which was a surprise to me actually. So here is if you look, yeah, this 10 to the power of minus 11, this is 10,000 femtoamps. So which probably everyone would consider a terrible recombination. But if you had 10,000 femtoamps on your localized contact, you could still reach above 24% efficiency. So maybe that was not a surprise to others, but it was a surprise to me. And it's a good surprise, because that means that high recombination is, so you can't go too much higher maybe, but at least around the 10,000 femtoamps, it's quite feasible to create a good solar cells with that kind of recombination. And that kind of goes against the passivated contact thing. So I think, yeah, so you either go for passivated contacts or you go for localized features. But at the moment, there's no reason to combine those both, the two things, unless you want to go beyond 24%. Right. And you see that a smaller contact is better, which makes a bit of sense if you consider all the crowding effects. Then it turns out the area fraction is actually similar for both kind of optimum conditions, but the smaller pitch, the smaller size is better, because then also the pitch is smaller and you lose less recombination due to surface recombination and bulk recombination. Yes, so the basic measures here is 24% is feasible with 10,000 femtoamps. And the other good thing is that contact resistance is actually pretty relaxed. So anything below 1 milliohms square centimeter, which is kind of a typical value you easily get, particularly for laser dope features, is very acceptable. It will not limit your efficiency. So contact resistance is not really a problem, unless you don't have contact at all, of course. But recombination is really the decisive thing which scales your efficiency you can get. All right, now you might argue, well, that was a bit of a stupid simulation, because I had no front surface recombination. I only had one polarity contact which was recombining, and the other one was perfect, and the bulk was intrinsic. Well, that's fair enough. So here's a second set of simulation, which is a bit more in detail. This is orientated along the 24.4% IBC cell efficiency we recently did at ANU. And well, it's a great thing. So it's a great thing because we can just take that baseline process. It's not really a baseline process, but it's actually somewhat reproducible, at least at the 24% level, and put our laser dope features in. And because it's at such high efficiency, we can really see the impact of the laser doped feature. So the clear idea is to use more or less the same IBC process and throw out all the complicated photolithography steps and replace them by laser doping and make a good cell out of it. And to see what kind of efficiency we can get with that concept, we now assume a few realistic assumptions for this particular ANU IBC design. So generation is actually the same. I didn't mention it, but it's like 42 milliamps per square centimeter, and assuming a typical generation profile you get under one sun condition. And now we assume 5 femtoamps recombination at the front and at the rear. We assume a 30 by 30 micron contact size, which is actually a feasible size to do our lab-based two-step process. So we do like 30 by 30 micrometer first, and then do a 20 by 20 micron opening, which is all aligned to that first doping. Well, we said that contact resistance is not really an issue for the cis set of simulation. We just neglect that. And what we vary now is the recombination property again of that. We also vary the bulk resistivity, because we are also interested what wafer we should take to make the best efficiency cell. And we also vary the bulk lifetime, because, of course, only very few of those wafers would be at an intrinsic limit. And there's one point about varying the bulk lifetime which is important to understand. So we not just set a fixed bulk lifetime or a fundamental short-grid hole about the bulk lifetime, but I will quote some bulk lifetime values, and they actually assume a short-grid hole recombination. So there's mid-gap short-grid hole recombination, so that they actually reproduce some sort of sensible injection behavior of the bulk lifetime. And the quoted values are representative of the effective bulk lifetime at 1E15 injection level, so what you would measure on the Sinton lifetime tester, for example. And now, again, as I said before, if you vary those things to have a fair comparison of efficiency, for each set of conditions you have to optimize again your geometry to get the maximum efficiency. So that's now quite a lot of iterations already. And there's one thing, because we now consider both contacts, N and P contact on the rear. And ideally you want to optimize the pitch independently, but you cannot do that within a unit cell because in one direction the pitch needs to be equal. But what you can do, you can change the number of contacts. So I created a set of different scenarios with different number of contacts for P and N. And for each set of scenarios, I optimized this kind of dimension here. So this kind of indirectly gives you an independent variation of the area fraction of both polarity contacts. So that should give you really the kind of maximum efficiency for each of those scenarios. So that ended being up, I don't know, 100,000 3D IV curves for Quokka to solve. And that took a couple of days, actually. But you could never do that in Centaurus or something, I think. And here's the results. I have to apologize, maybe a bit hard to see. But the dashed lines here correspond to N-type material, the solid lines to P-type material, and the different colors corresponds to different lifetimes. And on the left-hand side, I assumed 5,000 femtoamps per square centimeter for the recombination at the laser doped features, both for N and P-type, and on the right-hand side, 1,000. So this is very optimistic. So this is what you ideally get for a contacted, highly doped region. Could be even a bit lower for a properly doped region, but I think that's, if you would get 1,000 femtoamps with a laser, we would be very happy. And this might be more the realistic thing. So definitely with the two-step process, this should be feasible. So I would call this a realistic and this is an optimistic scenario. And there are a couple of interesting things to see. So first thing, regardless of the lifetime, and P-type is always better than N-type. Well, I think it's quite obvious if you think about it a second time, because the advantage of N-type is really that it has a better lifetime. So it's not quite not quite fair to compare same lifetime N to same lifetime P-type material. So it ends up that if you want to make an N-type cell, you need to have roughly 2 times the bulk lifetime to reach the same efficiency as P-type. And I think in practice, that's what you easily get from typical wafers. But anyway, so a couple of other things is, so even with the 1.5 or 1 ohm centimeter P-type, and I think particularly you guys are working on getting high lifetimes out of this industry standard material. So if you were able by hydrogen passivation or whatsoever, get a 2 millisecond P-type wafer, 1 ohm centimeter, you could reach up to 24% almost with such a wafer. And in the realistic case, it's still above 22% with a potentially very easy process. But of course, for a lab cell, we just go for an intrinsic wafer. So intrinsic in terms of doping and intrinsic in terms of lifetimes, which we can create by gettering. And if you go for highest efficiency, that's what you want to do in a lab cell. And it doesn't matter whether it's N and P-type, obviously, at high resistivity. All right, so as a summary, the efficiencies look good, so we can reach high efficiencies, easily above 22% and maybe up to 24%. So motivation is there to do research on that, at least for myself and a couple of others. And now, kind of next step, which was actually the first step, but anyway. So now we have to really go to the lab, make some laser doped features and see how they perform. And the goal now we have identified. So we now need to know what we roughly need in terms of J0 and air contact. So what we need to have is characterizations methods to extract those kind of properties from experimentally realized laser doped features. And yes, because you can't create a whole solar cell. So if you, for each parameter, want to create a solar cell, you would never succeed. So you want to ideally inspect hundreds of parameters, because there's quite a few things you can vary on in a single experiments, which you can't do on a solar cell level. So we need to have test structures, and this was actually the biggest part of the work to now, is to develop those kind of test structures, because the common characterization techniques, they not work well or not at all for localized features. So for example, QSPC, you need 4x4 or 3x3 centimeter area, uniform area. And also for transfer length method, you need a uniformly doped area to measure the contact resistance. And upscaling of that localized features is usually not allowed because I just said the edge regions is very important. So if you simply overlap your laser doped regions, you get rid of the edge regions and you might end up with a very good recombination. But in fact, if you do it localized, it's very bad. So we really want to measure the localized effects there. So this was not quite available in literature, so we had to develop some test structures. And they're basically all based on measuring some effective quantity, for example, a PL image or an integral resistance, and then do 3D simulations with Quokka mostly, and then you can kind of iterate to the feature, to the desired property you want to get out of the test structure. So here's the first example of what we do. This is actually one step back, so it's not doing the localized thing. But because the localized characterization is a bit more effort, what we start with is actually large overlapped areas because it's quicker, and if that doesn't work, you can be already sure that it doesn't work when you do it localized. So what we do is we create plenty of boxes on a 4-inch wafer actually by overlapping laser features. And if you now take a PL image of this one, and you can well describe this kind of scenario in Quokka because it has PL modeling also enabled. So you can simply simulate the same setup, and the only unknown, so if you make sure you know all the other properties of the device, the only unknown is then the recombination property of your laser doped region. So what you do is simply you make a sweep in Quokka, vary the recombination property, calculate the PL signal. So and with the resulting curve, you can interpolate the PL image and convert it into a J0 image of that sample. And that works pretty nicely, has been shown at the conference last year. It's a very easy thing to do, and it works nicely if the recombination is relatively high. So in this case, that very well applies. So you see that kind of recombination we get. So here's the 10,000 femtoamperes mark, which most of the features are around that. So and then you get simply an image, and you can, in this case, 120 laser parameters. You can very quickly assess the recombination property. There's a bit of an error to it, maybe 30%, which would be considered large when you do a proper recombination analysis. But for this kind of purpose, it doesn't matter too much. So this is the first step. And then we pick some parameters, and then we go to the localized analysis. So this is then a bit more involved, but it's basically the same thing. So instead of processing boxes with overlapping laser areas, we now process boxes with non-overlapping laser features with different pitch. So it's a regular array. It's a regular array of features within each box, and the bright boxes have a larger pitch than the not so bright boxes. And there's a couple of boxes for each pitch with different laser parameters. So in this example, we fit like 7 laser parameters on a 4-inch wafer, which is still plenty compared, and with different pitches, which is still plenty if you would do the same thing by QSPC, for example, which you could do. So that means for each pitch and laser parameter, you would have to symmetrically process a whole quarter of a wafer. And we also take care that we create kind of a smooth gradient of the PL images to not to suppress smearing effects or to make them less effective. And then, so for each box, we can run a 3D simulation, and again can predict the PL signal of that 3D kind of unit cell. And by matching it to the measured PL signal, we can again figure out the recombination at the contact. So here's another intermediate step. So what we figure out is actually not the J0 property, but we figure out the recombination current, not current density, or not saturation current density, but rather the recombination current for each pitch. And we also vary the illumination conditions. So what you actually get, you get a range of recombination currents at the same laser dope feature. And you can also extract from the device simulation the injection right at the contact. So you get a recombination current as a function of your injection at the contact. And then only as a second step, we look whether this fits, for example, to a J0 model. In this case, it does very nicely, but that's not usually the case. But what you also can see in this case, what is very nice, so you can essentially vary the injection level on the laser dope feature in 2 ways. So either you vary the pitch, that makes your overall laser dope combination, so increases the carrier density, but you also can increase the illumination, which directly increases the carrier density. So in the 2 ways, whatever you came up with as injection density at the feature, that should also end up to the same recombination current. So if you plot the different conditions in this graph, that means they should all lie on the same line. And they do. And this is kind of evidence that this method is accurate because it's self-consistent. It's actually hard to check against other methods because, as far as I'm aware of, there is no other method where you could extract the J0 of such a localized feature. So it's pretty hard to validate, but I think this is actually a good validation to be self-consistent in that respect. All right. So now we know how to sort out the local recombination. And the second thing is the contact resistance. So we actually do a similar thing. It's a bit easier maybe in terms of simulation modeling at least. So what we do, we create localized contacts, make a metal pad over it, and just measure the integral resistance. And again, by 3D, now it's simple current flow simulation of only the majority carrier. So the equations are much less nasty than for a 2-carrier device transport. We can also calculate or simulate the measured resistance and then vary the contact resistance until we get a match. And you see here just an example. This is actually an example on a diffuse surface, so it doesn't quite fit in there anyway, but you can do it also on an undiffused sample. And you see that it's pretty sensitive to the contact resistance, so you can pretty accurately, definitely below 1 e minus 3, get the contact resistivity. So, right, but yes, this only works if the polarity of your laser doped feature is the same as the bulk, because otherwise you create a diode. And if you have two opposing diodes, of course you can't measure any kind of IV curve or resistance. That should be perfectly isolating. So you can still do it and measure the shunt, which is important. But if you want to measure the contact resistance to a proper PN junction, you cannot do this structure. So what we do then is we actually create a diode which has the localized laser dope region of interest on the one side and a large area localized doping on the other side. And this basically can measure the IV curve, the dark IV curve of this device. It almost looks like an IBC cell, but the difference is that the PN junction is much more localized than you would do in an optimized IBC cell. And it turns out, so you can simulate that dark IV in Quokka as well, and you can then actually optimize different properties to it, which are of interest, which is the contact resistance, which is the main thing for this test structure. But it turns out it's also also sensitive to the recombination current density of those features. And you can actually also see the ideality, at least if the recombination is bad. And the good thing also about the test structure is it turns out that the other, particularly the recombination properties of the rest of the device, are not that important. It doesn't have a huge influence on the dark IV curve. So even with a bare rear surface and a not very good passivating film and high recombination here, which is also a bit unknown, this still extracts you accurately the contact resistance. Right, so here's an example what we did, now an experiment. So on the left-hand side, you see actually the solid lines are the measurements and the dots are simulations. They're only few because it's an iterative 3D simulation process, so you can't allow too many points because otherwise even Quokka gets too slow. But that's enough to fit the IV curve. And yes, so from these IV curves and the simulation, you can extract basically the contact resistance and the, I call it an effective recombination current density because it kind of lumps an ideal and non-ideal part. And you see that for most of our experimental features, we end up with pretty terrible recombination, particularly those ones. These are single-step, those were the first single-step processes we tried. So they have way too high. So that's, what was he said, maybe 1 million femtoamps. But there's at least one process which worked nicely. That's a 2-step process, which gives you actually below 1,000 femtoamps per square centimeter. And contact resistance is still good enough because it's below 1 e minus 3. So if you plot that in the efficiency chart I showed earlier on, you see that experimentally we have 24.5% efficiency. I mean, I know that's not really 24.5 measured efficiency, but it's a measured efficiency potential, I would know. But that really is a strong motivation, I think, that it's quite feasible to create those laser doped features to get to that sort of level of efficiency. And in the end, it might not be limited by the laser doped feature, but how you can achieve your surface passivation, things like that. All right, and now finally, I'll also show you the cells we did. So that was using the two-step process. So we first spin on phosphorus SOD, laser dope some features. We remove it, then spin on some boron SOD, laser dope some features. We do a front and rear silicon oxide, silicon nitride stack. Then we strip the front, texture it, passivate the front. And then we do the laser contact opening at the rear side, aligned to those previously doped regions. Then we do an HF tip to get away of some residual oxide. And then aluminum operation on patterning. And then we can measure the cell. And this is actually much easier if you compare that to you can imagine, to a full photolithography process of the same cell. This is like 10 steps less. Anyway, here's the results. So the good thing is it's a very good JSC, which is for an IBC cell already an achievement. So it's above 41 milliamps, so it's not only worse than the best IBC cells we made at ANU. The VOC is okay, 670 millivolt. Would have expected it a bit higher actually. But the problem really is the fill factor. So the best fill factor was like 70%, I think, 68, which is not very good. So we don't think it's recombination, particularly because the JSC is still good. And in an IBC cell, recombination would also decrease your JSC. We probably have like non-ohmic contact problems or non-ideal recombination going on at the contacts. And the reason for this is it was a very quick batch. We actually did that for the ARENA grants to have some cell results before the application deadline. So it was a very rush. And we didn't follow all of that nice procedure I showed you beforehand, but just made an educated guess on the laser parameters. It turned out to be not educated enough. So I think we know what to do better in the next batch. But still, I would think 90% for such a kind of, well, I don't like the word novel, but at least for a first try of this substantially different cell concept to others, I think 90% is actually not too bad. If you look at the historic efficiency on new cell concepts, you never start with 19%, so I think that's pretty good. And yeah, so I'll come to my conclusions. So we think at least that for research, I think this kind of all laser doped cell concept is attractive. In the end, if that all works, you end up with a very low thermal budget if you replace the thermal oxide with some other passivation. And because of the localized laser feature, it's low cost, but it's still high efficiency IBC design, up to 24%. And it turns out that the requirements on the performance of the localized laser doped regions are less strict than at least I expected it. I also want to point out I'm not suggesting here an industrial feasible SEN concept or anything, which many people tend to do. It's still early stage of fundamental research, but we have enough of insight to think it's interesting, and in long term it might get interesting for industry. And the main thing was to establish suitable characterization methods, and now we kind of finished that, so we're now ready to explore really large spaces of laser parameters, and we also have kind of a flexible laser lab, which we actually have access to this large range. And of course we want to make it better cell efficiency with that two-step IBC process, and we're pretty confident that we should be able to beat the 22% of Stuttgart, so have kind of a world record there. And also, but then the main part will form getting away from the two-step process, because that it's very questionable whether that's interesting for industry, but develop single-step laser processes for a really simple process. So with that, I want to thank you for your attention, and thanks for the IBC group at ANU, because it's really good to have a 24% kind of baseline cell process. They can throw something in and check how it behaves. And also, I want to acknowledge ARENA for the funding, particularly for my fellowship, but also a couple of other laser-related projects. Yes, thanks very much.
We have a question. I know that Ivan wants to ask something later, no? More question? Okay.
Thanks, Andreas, for a great talk. It was very informative. So you mentioned for your recombination modeling that you don't have anything really to compare it to. Theoretically, in the limit of a small pitch with the similar contact area fraction, you can assume that you get an effective recombination, surface recombination velocity from just assuming that there's no sort of 3D effects from carrier diffusion. Do you know when that sort of simple assumption diverges to the model that you need?
Well, yes. So I guess what you're referring to is that kind of analytical model which was first proposed by Bernhard Fischer, which actually quite a lot of people used for exactly the same thing. So they did effective lifetime measurements, not PL images, and then had an analytical model to predict the impact on the local recombination on the effective lifetime measurements. But there are a couple of traps in there. So, and I cited the one paper where I presented this localized feature extraction, and there are a couple of reasons there why this analytical model is quite limited. For example, it doesn't get you the injection level at the contact, but it always refers recombination to the average injection level in your device, which can be a huge error particularly if you have high recombination at the feature, because then the injection level at the feature is much lower. But there's a couple of other things. It uses an analytical expression for the series resistance of an equivalent structure, which has a bit of an error, which can propagate and amplify onto the final result quite a bit. So it can be done. It's a good first order thing, but it's not as general and accurate as this one, I would say.
Thanks, Andreas. There's the slide you showed with the simulations you did showing the different lifetimes versus bulk resistivity. Efficiency. Keep going back. Yep. And that one. I was wondering what it meant to have a different bulk resistivity for intrinsic.
Well, intrinsic just refers to the lifetime. So that just means intrinsic lifetime limited only by O'Shea and radiative recombination.
For the coloured, the nice sort of best case coloured plots, I didn't quite understand how the pitch fits into that.
Right, yeah. Well, the pitch basically isn't plotted. It's just to highlight that each point of this kind of plot is actually at a different pitch. And the pitch for each point is optimized for optimum efficiency. And you can kind of, so the trend goes that if you have higher recombination and better contact, you go to a higher pitch.
Sorry, one more quick one. On your photoluminescence image, you've got low lifetime areas around the edge of the wafer, is that correct?
Yeah.
So did you achieve that by limited passivation, or?
Well, this is actually unpassivated. So what we do is laser doping, and then we actually deliberately etch away the passivation or anything, because we are interested in the unpassivated case of the laser doping features. So this is simply a case of not having passivation in between there. There was never any passivation actually.
But that's still higher lifetime in your laser doped areas.
At some, yeah, that's interesting. Turns out, particularly if you use high resistivity wafers, and say you do an HF etch, you get quite good passivation. And if you did some crappy laser process before, that might be much worse. But the good features are never worse than the, or well, should not be at least.
Did you try Sun's VOC measurement on your cell? On that 90% efficient cell, you said that you think that it's most likely some resistance problem. So Sun's VOC would give you some good idea of what it could be with a better series resistance.
Let me think. It was all in a rush. I think we had that idea. Well, it was pretty evident also from the dark AV curve. I can't quite remember. We were very disappointed at this stage because we were clearly expecting 22 but 24%. And we were, oh shit. But after a while, I think it's actually not too bad, 90%. But no, we didn't do any detailed analysis. I think we know what the problem is, so we're not too interested to waste too much time in pinning down the actual problem.
Let's thank again Andreas for a great talk.